Good day to all of you. I hope you are all very well in both health and spirit. In this presentation, I will be talking about the use of DFT-based first principles calculations for fuel cell reactions. The use of fuel cells is one of the hot topics in catalysis because of hydrogen economy. It offers an enormous potential as an alternative source of energy for the future because it is environmentally friendly, can be easy to manufacture also, and at the same time, it has the potential use for portable power applications. The kind of fuel cell that I'm particularly interested with is direct borohydride fuel cell. In this presentation, I will show you how to get insights from DFT calculations towards the rational design of catalysts for borohydride oxidation. I am Ryan Arevalo. I am a Blake scientist hosted by the University of San Carlos in Cebu City. The first part of my presentation would be about the adsorption structure of borohydride and how you can use it as a descriptor for the selectivity towards hydrogen evolution or the direct oxidation of borohydride. The next one would be about the adsorption energy of borohydride as a descriptor for overpotential requirement for oxidation. The third one is a mechanistic study of the overall reaction of borohydride oxidation. And then finally, I will show you how we gained insights for catalyst design. Direct borohydride fuel cell is an alkaline-based fuel cell that uses aqueous borohydride solution as the anode fuel and oxygen at the cathode. Over an electrocatalyst that is selective towards the direct oxidation of borohydride, each borohydride ion is capable of liberating 8 electrons to the electrode via this suggested half-anodic reaction. Now, the borohydride molecule can undergo a direct oxidation process that liberates electron, or it could also undergo a hydrogen evolution reaction that produces hydrogen gas. For the case of borohydride fuel cell, it is the direct oxidation reaction that is desired over the hydrogen evolution reaction because this particular reaction limits the Coulombic efficiency of borohydride, and at the same time, the hydrogen gas produced from the reaction can cause some mechanical failures. What do we know from experiments? In terms of Coulombic efficiency, it was found that when you use gold as an anode catalyst for this particular fuel cell, almost 8 electrons per borohydride ion is produced. So we say that there is high Coulombic efficiency. And at the same time, it was found experimentally that there is no hydrogen evolution. However, for the case of platinum, there's only about 4 electrons liberated per borohydride ion. So we say that there is low Coulombic efficiency, and at the same time, there is high hydrogen evolution. Here you see very well that when there is no hydrogen evolution, high Coulombic efficiency is promoted. However, when there is high hydrogen evolution, there's only low Coulombic efficiency. Now, in terms of the overpotential requirement for the oxidation of borohydride to occur, it turned out that there is high overpotential requirement for gold, while for the case of platinum, there's only low overpotential. Overpotential is essentially the difference between the thermodynamically determined potential at which the oxidation will occur and the potential at which the oxidation actually occurs experimentally. High overpotential means that there is high energy loss, while low overpotential means that there is low energy loss. So the desired catalyst is the one that has a mixture of characteristics between gold and platinum, such that it should promote an almost 8 electron per borohydride ion or high Coulombic efficiency, just like the case of pure gold, and no hydrogen evolution. But at the same time, we would like to get the low overpotential requirement characteristic that was experimentally seen for the case of platinum. So we conducted DFT calculations in order to understand the difference in the catalytic activities and selectivities of gold and platinum so that we can gain insights for the rational design of catalysts for borohydride oxidation. Let us look at the adsorption structure of borohydride on gold and platinum. Interestingly, we have found that when you optimize a borohydride and ion on gold and platinum, borohydride actually adsorbs molecularly for the case of gold. However, for the case of platinum, it adsorbs dissociatively. Now, these dissociated hydrogen atoms on the surface can either undergo a hydrogen evolution reaction that produces hydrogen gas. This is an associative desorption towards the reduction of hydrogen gas, or it could react with an aqueous OH negative species, producing aqueous water molecule and the liberation of an electron. The efficiency of borohydride fuel cell then depends on the competition between these two reactions. The one that has higher efficiency is the one that promotes the oxidation of hydrogen atom rather than the hydrogen evolution reaction. We simulated these two reactions on the surface of platinum, and this is what we have found. I show here the free energy change for the two reactions as a function of electrode potential with respect to the normal hydrogen electrode. I show here the results for the case of 1/9 monolayer and the 1 monolayer case, that is for the coverage of hydrogen atom. Here we can see that for the case of the oxidation reaction, the oxidation is, the free energy change is negative, which means that oxidation can occur at these particular electrode potentials. When the coverage of hydrogen atom on the surface is higher, we see that the oxidation reaction can actually occur at the lower electrode potential. Interestingly, for the case of the hydrogen evolution reaction, for a small coverage of hydrogen atom on the surface, the hydrogen evolution reaction has a free energy change greater than 0 or positive, which means that it is an endothermic process. While for the high coverage of hydrogen atom on the surface, the hydrogen evolution reaction becomes exothermic. So we say that hydrogen evolution is favorable at high coverage of hydrogen atoms. So if we compare the cases of gold and platinum, since the adsorption of borohydride on platinum is highly dissociative, there's a high coverage of hydrogen evolution. There's a high coverage of hydrogen atoms on the surface that lead to hydrogen evolution. So in terms of the adsorption structure, we would like to have a catalyst that promotes the molecular adsorption of borohydride on the surface rather than the dissociative adsorption. And we can relate that to the Coulombic efficiency of borohydride oxidation. For the case of gold, there's high Coulombic efficiency because there's no hydrogen evolution, which we can theoretically attribute to the molecular adsorption of borohydride on the surface. While for the case of platinum, there's low Coulombic efficiency because it is very susceptible to hydrogen evolution, which can be due to the highly dissociative adsorption structure of borohydride on the surface. So this is what I've said earlier. The molecular adsorption of borohydride can promote no hydrogen evolution, while the dissociative adsorption promotes high hydrogen evolution. We computed the adsorption structure of borohydride on these transition metals, and we have found that for the transition metals that are denoted by this red color in the periodic table promote dissociated structure of borohydride. Now these coinage metals here, copper, silver, and gold, promote a molecular adsorption that is close to the gas phase adsorption BH bond length of borohydride, while for these particular metals here, cobalt, nickel, ruthenium, rhodium, and osmium, the adsorption structure is still molecular, but the BH bond lengths are already elongated. Now let us look at the adsorption energy of borohydride on these surfaces. Since borohydride is an anion, its adsorption on the surface can be modeled as an oxidative process. Here, you have borohydride anion in the aqueous phase, and you have water molecule that is initially adsorbed on the surface. So the oxidative adsorption of borohydride is taken to require a substitution of an initially adsorbed water molecule on the surface, liberating an electron. The adsorbed species is of this form. Here, x plus y is equal to 4 because there are 4 hydrogen atoms in a borohydride molecule. When x is equal to 4, y is equal to 0, you have a molecular adsorption. For the case of platinum, x is equal to 1 while y is equal to 3. You have a dissociative adsorption. I show here the free energy change for the adsorption process given by this equation for the case of platinum and gold. For 2x2 adsorbate coverage as well as the 3x3 adsorbate coverage is a function of electrode potential. One of the first observations from this graph is the effect of adsorbate coverage. For the case of platinum, since borohydride dissociatively adsorbs on the surface, the distance of separation between the borohydride dissociated fragments is really just small, and so you have the effect of repulsive interaction between the dissociated borohydride fragments. While for the case of gold, since borohydride molecularly adsorbs on the surface, the distance of separation between the borohydride molecules on the surface is large enough so that the effect of repulsive interaction between the neighboring borohydride molecules is really just small. For the case of pure platinum, here you see that the reaction is exothermic, or delta G is negative for all relevant potentials. So we expect the dissociative adsorption of borohydride and platinum to proceed at all relevant potentials. Well, for the case of gold, the free energy change is negative or exothermic only at these values of electrode potential. Now, interestingly, these calculated values are in stark numerical agreement with those reported in the experiment. In this voltammetry experiment performed by Professor Gyenge at the University of British Columbia, it was found that borohydride oxidation actually starts at around negative 0.20 volt versus NHE. In this cyclic voltammetry curve, an A to peak is observed at this electrode potential corresponding to 0.20 volt versus NHE, which they attributed to the direct oxidation of borohydride. Now, the difference between these oxidation potentials for gold and platinum catalyzed borohydride oxidation is related to the values of the adsorption energies of borohydride on these surfaces. For the case of gold, the adsorption energy is actually just weak, while for the case of platinum, the adsorption of borohydride is strong. That is why the oxidative adsorption proceeds at all relevant potentials. Therefore, in order for us to attain a low overpotential for the new catalyst, we would like to have a catalyst that promotes the strong adsorption of borohydride on the surface, just like the case of pure platinum. So the results that I have presented so far only concern the initial adsorption of borohydride. Now let us look at the overall reaction process, wherein borohydride oxidizes towards the final product, which is a metaborate. Here is a proposed model reaction coordinate. The model reaction coordinate is defined this way. You have borohydride in the aqueous phase plus 7 OH molecules in the aqueous phase plus water molecule that is initially adsorbed on the surface. And then you have the adsorption of BOXHY species and the other terms here. Here the values of x are from 0 to 2 and the value of y are from 0 to 4. The relative free energy change for this particular reaction for a particular COX, I think this is wrong. This should be BOXHY plus ZH species is simply the difference between the free energies of the product and the reactant. So here, the delta GR for a particular adsorbed species will give us the relative free energy of that particular adsorbed species on the surface with respect to our reference state, which is the aqueous phase borohydride and ion. I show here the adsorption structures of BOXHY type molecules that we have considered in this study. Here we see that BH3 has the same adsorption structure as BH4. I also show here the adsorption structures of other non-oxygen containing BH fragments. So for the case of boron atom, it adsorbs at the hollow site. So the other adsorption structures are shown here. I also completed the adsorption structure for the case of water molecules. So these adsorption structures were identified to be the optimal adsorption structures among several possible configurations of these molecules on the surface that we have explored. Then using the model reaction coordinate that I have shown earlier, we can plot the relative free energy of particular adsorbed molecules on the surface towards the final adsorbed molecule, which is a BOH3, which is essentially the hydrated form of metaboric BO2 negative. This free energy diagram is evaluated at two electrode potentials. Negative 1.24 volt versus Ng is the equilibrium potential for the reaction. Here you see that the initial oxidative adsorption is endothermic, while at this particular electrode potential, negative 0.15 volt versus Ng, you have the initial oxidative adsorption of borohydride to proceed exothermically. Subsequent to the initial adsorption of borohydride, you see that all elementary steps toward the final product proceed downhill in energy. In my presentation so far, I have only talked about borohydride reactions on gold and platinum surfaces. These surfaces were chosen as benchmark systems because these are the conventional catalysts that are being used in the industry. Let us see how our insights from DFT calculations from our study on borohydride reactions on gold and platinum can be used for designing catalysts for borohydride oxidation. We have seen that for the case of gold and platinum, weak adsorption results in high overpotential, while the dissociated structure results in hydrogen evolution. Therefore, we would like to avoid this by designing a catalyst that promotes the strong adsorption of borohydride in order to promote the low overpotential, and at the same time, we would like the catalyst to promote the molecular adsorption structure so that hydrogen evolution can be avoided. We calculated the adsorption of borohydride on these transition metals. We have found that for the case of 3D transition metals, such as chromium, manganese, iron, cobalt, and nickel, the adsorption of borohydride is very strong, while for the case of silver and gold, the adsorption energy is just weak. So we propose alloying gold with 3D transition metals. These are the models that we have used for our gold-based alloys. Here, gold is the base metal, and we introduce 3D transition metals as the alloying components. We considered different terminations on the surface and found that the surface energies are almost the same for these surfaces. We also chose the gold 3M alloy because it was successfully synthesized in the laboratory with L12 crystal structure, and experiments have also shown that these gold-based alloys have such ratio of gold and 3D transition metal. Let us analyze the adsorption structures of borohydride on these alloy surfaces. I show in this table the BM bond length, or the distance of separation between the boron atom in borohydride and the alloying metal M in this column, as well as the average BH bond lengths of borohydride. We see that for this second group of alloys, borohydride adsorbs at a closer distance to the surface compared to the first group of alloys. Accordingly, the BH bond lengths of borohydride are more elongated compared to an almost gas phase borohydride structure for the case of the first group of alloys. In order to understand this, we analyze the local density of states projected on iron and cobalt alloys to represent the first and the second groups of these alloys respectively. I show in this curve the partial density of states projected at the surface parallel components of the D-band, the dxy and the dxxyy components, as well as the components of the D-band that protrude out of the surface, such as the dzzz component, dyz, and dxz components. Here we see that for the case of both iron and cobalt, there's a change in the partial density of states between before and after the adsorption of borohydride, while for the surface parallel components, the change in this particular component of the D-band is only seen for the case of cobalt. We think that this interaction with the surface parallel components of the D-band for the case of cobalt and nickel contribute to the elongation of the BH bonds of borohydride. Accordingly, we can say that these components of the D-band can promote the transfer of electrons to the antibonding orbital with respect to the BH bond length of borohydride, resulting in the elongation of the BH bond length. Now let us look at the adsorption energies of borohydride on these alloy surfaces. We found that borohydride seeks the alloying metal M, unlike the case of pure gold, wherein the interaction is essentially through the bonding between hydrogen atoms of borohydride and gold atoms on the surface. Interestingly, the adsorption energy is increased by 0.33 to 0.58 electron volts compared to the case of pure gold. The magnitude of adsorption energies are tabulated in this table. In order to understand the increase in the adsorption energy of borohydride on these alloyed surfaces, we analyze the density of states of the system. In this first figure, I show here the density of states projected on pure gold, which is the red plot, as well as the gold-cobalt alloy to represent the alloy systems, that is the black plot. Here we see that for the case of pure gold, the D-band is fully occupied. But for the case of the alloy systems, there is an emergence of unoccupied states near the Fermi level. In this particular figure, I show the local density of states of gold-cobalt alloy projected on gold atom as well as cobalt atom on the surface. We can see from this figure that the low energy region is due mainly to the D-band of gold, while the high energy region is attributed mainly to the D states of cobalt. So here we can clearly see that the emergence of the states near the Fermi energy is due to the D-band of cobalt. So we say that upon alloying gold with a 3D transition metal, the D-band of the metal is upshifted. When this hybridizes with the sp states of borohydride, this formation of unoccupied states with respect to the fully occupied D-band of pure gold results in the upshifting of the derived antibonding sp-d states, which leads to stronger adsorption. I show here the sp states of borohydride when it is adsorbed on pure metal, which is the green plot, as well as when it is adsorbed on gold-cobalt alloy. I also show in the inset figures the partial charge density plots projected at these particular peaks. For the case of pure gold, we see here that the occupied states just below the Fermi level have antibonding characteristics with respect to the adsorption of borohydride. However, for the case of the alloy systems, the occupied states just below the Fermi level have bonding characteristics. On the other hand, the unoccupied state just above the Fermi level has an antibonding characteristic. Because of this, there's a dominance of an attractive interaction between borohydride and the surface for the alloy systems, which leads to the stronger adsorption of borohydride on the alloy systems compared to the case of pure gold. Accordingly, if we do the same plot for free energy change for the adsorption of borohydride on the alloy surfaces and pure gold, in the same way that I have explained earlier, we see from this graph that for the case of the alloy systems, the oxidation of borohydride can proceed at a lower electrode potential compared to the case of pure gold. This calculation is in agreement with an earlier reported experimental result showing that the oxidation of borohydride on gold-nickel alloy can proceed at lower electrode potential compared to the case of pure gold. Comparing the overall reaction of borohydride on pure gold and the alloy surfaces, here we see that at an electrode potential of negative 0.60 volt with respect to the normal hydrogen electrode, all elementary steps leading to the complete oxidation of borohydride to the final product proceed downhill in energy. You can see it clearly for the case of the black plot here, which is for the alloy of gold and cobalt. For the case of pure gold, at this particular electrode potential, the red plot shows that the initial oxidative adsorption of borohydride still proceeds endothermically. To summarize the presentation, I have shown that through our study on benchmark systems, in particular gold and platinum catalysts, we have found that the weak adsorption of borohydride results in high overpotential, while the dissociated structure results in hydrogen evolution. So we have used this observation in order to design new catalysts. We have proposed alloying gold with 3D transition metals. Now this alloy of gold and 3D transition metals promote the strong and molecular adsorption of borohydride with thermodynamically favorable overall oxidation. This is due to the upshifted D band of the new system with respect to the case of pure gold. So that is how we can use DFT calculations for fuel cell reactions. I hope that this particular study will stimulate further interest in similar systems, and you have somehow gained some insights on how you can use first principles calculations for your research topics. Thank you for your kind attention.